So we're looking for a group automorphism of the group Z mod 4 that happens to map 2 onto itself. So I'm going to show you the group automorphism that does that. 0, 1, 2, 3. So this is the underlying set of our group, and here's the same set. So this is what we're going to map it onto. So the set automorphism that underlies the group automorphism that fixes 2 is this. That's it. It maps 2 onto itself, it maps 0 onto 0, it maps 1 onto 3, and 3 onto 1. That is a group automorphism of this group, and I'm going to prove to you that it's a group automorphism of the group. So we take our original Cayley table, 0, 1, 2, 3, 0, 1, 2, 3, and this had 0, 1, 2, 3, 1, 2, 3, 2, 3, 3, 0, 0, 0, 1, 1, 2. Okay, so that was our original composition table. Now, let's do this group automorphism. So, 0, 1, 1 goes to 3, so put 3 here. 2 stays at 2, 3 goes to 1, 0, 3, 2, 1. So, 0 remains at 0. 1 goes to 3, so 3, 3. 2, 2, 2. 3 goes to 1, 1, 1, 1, 1. 0 goes to 0. 1 goes to 3, and 2 remains as 2. Now, so this is the property of group automorphisms, that what they effectively are is a relabeling of the elements of the group. All we're doing really is we're taking this element and we're relabeling it as 3, and we're relabeling this element as 1, and when you relabel the composition table, it doesn't actually make any difference. If that's the case, then it's called a group automorphism. So look at these two composition tables and look at them a bit more carefully. Are they in any way different? Find me a composition of check all 16 compositions. So, for instance, take 0 composed with 0, it's 0. In this one, 0 composed with 0 is 0. 1 composed with 0, 1 composed with 0 is 1. 2 composed with 0 is 2. 2 composed with 0 is 2. 3 composed with 0 is 3. 3 composed with 0 is 3 in this one. 1 composed with 0 is 1 composed with 0. So that's 1. 1 composed with 1 is 2. 2. 1, right, I'm getting confused now. 1 composed with 2 is 3. 1 composed with 2 is 3. 1 composed with 3 is 0. 1 composed with 3 is 0. 2 composed with 0 is 2. 2 composed with 0 is 2. 2 composed with 1 is 3. 2 composed with 1 is 3. 2 composed with 2 is 0. 2 composed with 2 is 0. 2 composed with 3 is 1. 2 composed with 3 is 1. 3 composed with 0 is 3. 3 composed with 0 is 3. 3 composed with 1 is 0. 3 composed with 1 is 0. 3 composed with 2 is 1. 3 composed with 2 is 1. 3 composed with 3 is 2. 3 composed with 3 is 2. So you see that every single composition in this table is exactly the same in this new table. It hasn't changed a thing. It's the same group. It's the same group. It's just relabeled. Each of these elements have been relabeled, and it hasn't made any difference. So it is indeed a group automorphism, and you can check. You can try checking that A composed with B. If you take A composed with B, so for instance, say A is equal to 1 and B is equal to 2. So 2 composed with 1 is 3. So AB is 3. So phi of 3 is 1. So this is 1. And now what we need to check is that this is equal to phi of A composed with phi of B. So phi of A, phi of 1 is 3. 3. Composed in this new composition here, but the compositions are exactly the same. Composed with B, phi of B was 2. So 3 composed with 2. 3 composed with 2 is 1. So they're exactly the same. You can do it either way. You can compose them in this one and then transform it, or you can transform them and then compose them, and it doesn't make any difference. So that's evidence that this is a group automorphism. Right, here's the killer. That if we take our equation, x composed with x is equal to 2, this is truly true. If you take for the solutions of x, this is true, this relation is true. So we know the solutions are 1 and 2. So when you compose 1 with 1, it gives 2. If you compose 3 with 3, it gives 2. So for the solutions of this equation really is true. So therefore, if we transform this side of the equation, it will be the exact same as if we transform this side of the equation, won't it? Because these two things really were equal, providing x is a solution to this equation. Therefore, if you transform them, it must still be the same thing. So the equation still holds if we transform them. Now we use the fact that it's a group automorphism, because we can split this into 5x composed with 5x. And I have proven to you that that is exactly the same as this. And because it's a group automorphism. So 5x composed with 5x is equal to phi of 2. What is phi of 2? Phi of 2 is 2. This is the mapping, phi. Up here. So this is equal to 2. So we have that phi of x composed with phi of x is equal to 2. What is phi of x? Phi of x is some element of the group. We could give it the symbol y. So we want y to satisfy that equation. But this equation is exactly the same as the original equation we had. This says some element of the group composed with some element of the group is equal to 2. This says some element of the group composed with some element of the group is equal to 2. So what we've shown is that if x is a solution, phi of x must also be a solution. Is a solution. So if 1 is a solution, phi of 1 is a solution. And what is phi of 1? It's 3. So what we've done is we've found a mapping, a morphism that morphs 1, a root of this equation, into 3, which is another root of the equation. And this mapping will always map roots of the equation into roots of the equation. So if we knew 3 was a root, it would map phi of 3 is also a root of the equation, and phi of 3 obviously is 1. So how is this more useful? Where is this going? What can we use it for in the common algebra, the one that everyone learns in school? So if you've, say, got some huge equation, say 5x squared plus 6x plus 7 is equal to 0, and you want to, and say you've got one of the solutions to this equation, so you've got, say, x is equal to something, so you've got a solution and that's x, then if we can find a mapping that is a field automorphism, it's now a field automorphism, which means if it's a field automorphism, then a plus b is equal to phi of a plus phi of b, but also phi of a times phi of b is equal to phi of a times phi of b. So that's far more difficult to find than our group automorphism. But if you can find such a mapping, a field automorphism, then you can act this field automorphism on both sides of this equation, and it splits it into this. Oh no, what have I done? Phi of 6, phi of x. So we're just operating it on both sides. We've split up the addition because of this rule here, because it's a field automorphism. And now what? If we say, if this phi fixes 5, it fixes 6, it fixes 7, and it fixes 0, then we get this equation. 5 phi of x squared plus 6 phi of x plus 7 is equal to 0. So therefore, what have we found? If x satisfies this equation, phi of x also satisfies this equation, providing phi is a field automorphism which fixes 5, 6, 7, and 0. So it has to fix the coefficients of the equation. This is what complex conjugation is. Complex conjugation is a field automorphism. So it satisfies these two properties. You can check that for yourself. So all you need to check is that phi of two complex numbers added together, if you complex conjugate two complex numbers added together, it's the same as complex conjugating one of the numbers and then adding it to the complex conjugate of the other number. And you can also check that phi of two complex numbers times together is the same as complex conjugating one of them. In fact, should we prove this? So we've got two complex numbers. We're taking the complex conjugates, so of a plus bi plus c plus di. Those are our two complex numbers. We've added them together, so we'll get a plus c plus b plus di. And then we complex conjugate it, so it'll get a plus c minus b plus di. So there's our complex conjugate, and you can see that if you complex conjugate each of these separately, see, there you go, minus, you've complex conjugated them separately, and now add them together, it will be exactly the same as that. I'm going to cut the video there, and we'll continue this